let us keep going. If you opened up the document online, I tried to make some edits again, and it didn't want to save. But it's not that it's a big difference. I did add end pyramids if you're writing ahead, and that's okay if you've got it. And if you don't, it's not a big deal. Okay, so yesterday we talked about food chains, right? Straight, nice lines. Again, producer at the bottom, working our way up, and our arrow points in the direction in which that energy is flowing, right? It starts down here, and it works its way up to those top consumers. There are other ways in which we can express the flow of energy, and that is using something called pyramids. Now, before we do that, let's define a term, a very important term, and let's define an ecological niche. You may have heard this term before. Again, some of you have been indicating to me that you've done food chains and food webs, right? So some of you may have done this in detail in the past, which is awesome. Have you talked about a niche? If some organism has a niche? No, yes, no? It's simply the entire role of that species within the ecosystem, all right? It involves where it lives and what it eats, and its behavior and how it interacts with other organisms, and that's the term that then we use to describe that. So this is really just a definition of this idea of a niche, and not only is it just the food, but where it lives, like I said, and how it behaves and how it interacts with other organisms. So it's kind of like the whole thing, the whole way in which that particular organism behaves. All right. And you can see there's a picture of a bear there. Again, I'm not a fan of putting random pictures, but that one kind of makes sense, right? If you've ever, been camping or been to a cottage way up north, you know to be aware of the bears and to make sure that you don't necessarily go out on your own without the appropriate, noise and protection. And that's because bears have a particular demeanor, right? They eat on the berries, they move around through an ecosystem, they can be aggressive if they have young, that type of stuff. And so that entire way in which the bear behaves and what it's doing is called its niche, its place in the ecosystem. Okay. So that's kind of a random place to put that particular definition, but I'm kind of following through the textbook as I go along, and that's where they've kind of put it. So the next thing I want to talk about is how energy moves through it. We've talked a little bit about it. Can I move ahead? Are people using devices if they're running behind or ahead? I can go back. If you're not using a device, it's fine. It's not a problem. I'm not concerned. And I don't mind if you write at different speeds on your devices, but try to listen to what I'm saying at the same time. I know it can be difficult, but try to listen so that if you have any questions, you know when and where to ask it. Are we good to go? Good to go? So we've talked about energy transfer. The energy moves up a food chain. And we're kind of reminding ourselves of that here. The producers use sunlight energy to convert abiotic factors into carbohydrates, or what I've been calling sugars. Carbohydrates are just a fancy name for sugars because that molecule contains carbons, hydrogens, and oxygens. That's what the word carbohydrate means. And when herbivores feed on these producers, they don't necessarily receive all of the energy, all right? And that's what we want to express. A food chain is sometimes too simple, all right? So we need more detail to express what's happening in the food chain. So whenever that, what were we saying? Grasshopper eats some of the grass, it doesn't receive all of the energy that's in that grass. There's always waste and energy that doesn't go into the new organism. So there's less and less energy as you move up. Now, on the slides, and I want you to kind of just watch a little bit, maybe leave some room, because I'm going to draw some examples of these pyramids, and I'm going to put it on the chart paper, all right? So if you're writing ahead, after the trophic levels, when I get to talking about pyramid of energy, I'm going to draw a pyramid of energy on the chart paper for you to draw in your notes. And it's going to be a little different than this one, just because I want to make it simpler than that. Same with the pyramid of numbers. I'm going to draw a simpler version, and same with the pyramid of biomass. So when you get to those examples of pyramids, leave a little room to draw an example pyramid, okay? All right? Yep. I am going to have in my food chain 1, 2, 3, 4, just like this one. All right, I'm going to have 4 levels. Okay. Again, we've already been introduced to trophic levels. So this is kind of a review. So I'm going to bring that up there. Don't write this little bit on the side. It was part of the note, but it's an information that I don't think is important, but I wanted to leave it there just for a reminder to myself. If you already wrote it, it's not a big deal. If you already wrote it, it's okay. Remember, we've already talked about trophic levels, and here they are. And I'm actually going to write down our trophic levels on the chart to begin my kind of summary of what's going on. So I plan on using lots of chart paper. So trophic levels. Does anybody remember what that trope stood for? Yep. Just stands for food. Remember, it just stands for food. So trophic levels is just food levels. And again, down at the bottom, we've got producer. And you don't need to write this down. This is just for me a reminder and you a reminder. Producer. All right, we move up and we've got primary consumer. We move up, we've got secondary consumer, and we move up and we've got, I'm going to put tertiary, I'm going to put TERT, short form for tertiary consumer, or the third consumer, and that's what we call our trophic levels, all right? And that's nothing new. All right, trophic levels. And the fan's going to blow on it, so I need another magnet. Okay? All right? And it can go up. It depends on how many things are in the food chain. All right. So, when we move up a trophic level in a food chain, some of the energy is stored. So it goes into storage like wood. Talking about a hunk of wood. Not all organisms want to eat the wood. Termites would, but termites would, but not all organisms do. So that isn't available for the next level. All right. Some of it's converted to heat. Remember, I said that's a type of energy, right? At the very beginning of this class, and yes, I'm recording this, Kyla said that Parker is responsible for all the heat in the room because he's hot. That's right, Parker's hot. And he is. But really, we all are. If I took that thermometer and I put it up against my forehead, it would be very similar to everybody else's. That's body heat. But what I'm saying is, that energy that is heat that's coming off of our bodies or off of a lower level animal, that energy is lost. That energy can't be moved to the next trophic level. So if a lion then decides to eat Parker, right, this afternoon, that heat that he's giving off, because he's hot, is not available to the lion because heat is lost to the air. It just goes into the air and it warms up the air, okay? All right? So there's always that heat energy which is unavailable. Yep?
That's why it's hotter and like more people are.
Correct. They're supplying energy to the room. That's right. This is a physics law. This is actually called the 0th law of thermodynamics. And there's a great long story to why it's called the 0th law and not the 1st law. It's because they they discovered and explained the first law before they knew about the 0th law. So they had to go backwards in numbering them. But the 0th law of thermodynamics, and by the way, thermodynamics simply means the movement of heat energy, is that hot things lose heat to their cold surroundings. And it just happens naturally. And Dahlia's looking at me as if to say, well, of course it does, right? A hot coffee always gives its heat off to the air surrounding it. The air never gives its heat back to the coffee and makes the coffee hotter spontaneously. That never happens. If you think about it, you might think, well, that's obvious, right? That's the way the world works. But according to laws of physics, there is no reason why it couldn't go the other way. The air has heat. It could push it into the coffee and just spontaneously make the water boil, but we never see that happen. So it's a law. We only see hot things get cold, all right? So things like body heat naturally lose energy to their surroundings. You can't stop it. There's no stopping that. Okay, that's my little fix of physics. All right, so this decreases the biomass, the total mass of living things available at the next level, because that energy has to come from some of the stuff of the previous level. So there's always less and less stuff and less energy as you move up a food chain. Okay, pyramids. So pyramids are simply a way in which we display this information. And now I'm going to get my markers ready because we're going to draw some different pyramids. So there's different ways in which we can express the pyramids. We could do it by how much energy is available at each level. All right? So because the energy stored in chemicals, again, I'm going to divert into chemistry, we have ways in which we can calculate all that stored energy in all of the chemicals. That's in my grade 12 course on thermodynamics. We study how much energy is stored in chemicals. So we can mathematically determine how much energy is in the grass. That's at the bottom of the pyramid. And then we can determine how much energy is at the next level of that pyramid if we have something like, and I'm going to have a rabbit eating the grass. So we can determine how much energy is in that rabbit. All right? So we can have a pyramid that describes the energy that's moving up in the food chain. We can have a pyramid that describes just the numbers. How many blades of grass do the rabbits eat? Or plants of grass, I guess. So we can simply count the numbers. All right? And then there's a third one, and I can't remember what it is. What's the third one? Oh, of mass. What's the mass of all the grass that the rabbits eat? And then the mass of all of the rabbits at the next level. So that's three different ways in which we can express it. The first one I have is going to be a pyramid of energy. Now, you can write that information, okay? And then I'm going to show you the pyramid that I want you to draw. Now, as you're doing that, I'm going to write simply the food chain that I want to analyze. And I took this off of a graphic that I have in here, but I want it to be simple for you to draw. And my simple food chain is going to be grass. And then we're going to have rabbits eat the grass. And then we're going to have a fox eat the rabbit. And then we're going to have a wolf eat the fox. Okay? All right? So this is my example food chain that I'm going to apply to the pyramid that I'm going to get you to draw. See what I'm saying? And I don't know if you notice a trend here, but I'm attempting to put them all nicely in a row so you can compare what I'm talking about, right? So the grass is the producer, right? The rabbit's my primary consumer, etc., etc. All right? Okay? So if we were doing a pyramid of energy, so in my pyramid of energy, at the bottom, I'm going to put a big rectangle down here, and it's going to represent the energy that's in the grass. All right? Now, if this was a real pyramid of energy, I would have a unit that is called joules. Okay, we measure energy in a unit called joules. It's named after a scientist who did a lot of work in the idea of energy. Again, this is physics and chemistry, so I am comfortable with this. His name was James Prescott Joule. He was a very smart guy. So we honor him with the unit joules after his name. But I really don't know how many joules of energy would be in that grass. We could do it as chemists. We could try to gather up all the grass that a rabbit would eat, and we could then take that grass and combust it, burn it. We could then heat some water with that burning grass, and from the increased temperature of that water, we can do math, and we could figure out exactly how many joules was in that grass. All right? That's called thermochemistry. That's grade 12 chemistry. It's good times. It's fun. All right? I'm not going to do that here. We're simply going to say that the grass is going to have 100% of the energy that came from the sun. All right? Not all the sun's energy, but that little bit we talked about at the beginning, the 0.2 something percent. So I just want to give you the impression of what happens as we move up. As we move up, next, we're going to have our rabbits. And we mentioned this on the first slide. It turns out that only 10% of the energy available actually makes it into the next level. 10% goes underneath it. My pyramid isn't actually to scale. If this was 100 centimeters long, my next one would end up being just 10 centimeters long. So I'm a tiny little sliver. You see how the pyramid's getting very tiny very quick. But I'm not going to draw it that skinny. Okay, it's going to be 10% its value each time. And as the foxes eat the rabbits, it's going to be 1% of the original energy, because it's going to be 10% of the previous level. So you'll notice it gets really skinny really fast. We lose a lot of energy very quickly as we move up. That says 1%. Fox is 1%. Okay? Which means as we then eventually get to the wolf, it's going to be a really skinny rectangle. And I'm just going to put a label here, wolf. All right? And this is going to be 0.1% of the original energy. Okay? All right? So as you move up the pyramid, the amount of energy available decreases rapidly. Yes? Correct. In order to survive. Correct. Now, if we want to talk about something that's very topical right now, instead of having grass, rabbits, fox, and wolves, we could have soybeans or corn, cows, right? And then people, because I like steak, right? Now, that means that people, like myself, eating the steak, is really only using a small percentage of the soybeans' energy. We're really only using 1% of the energy of the soybeans. Okay? Right? Because we're taking the energy from the cow. If we took the cow out of the way, all right, and we just ate the soybeans, like in tofu, we'd be able to feed a lot more people, because we would be using a lot more of the energy by removing the cow. Does that make sense? Okay, now, in the news right now, the I can't believe it's not meat burger or whatever you call it. You know what I'm talking about? Okay, it's been in the news. Exciting stuff. All the vegetarians in the world are loving it. Well, actually, they're not, because they still don't want to eat it. It tastes like meat. What they've done is they've created a vegetable-based, I don't know if it's soybean-based, and then they've created a chemical that smells and tastes like blood. And when you cook it, it smells and tastes like cooked blood, and that's what makes a steak taste so good. You don't know it, but that's why you crave a burger and a steak, because of that hemoglobin that's cooked in such a way and it makes it taste phenomenal. Well, to me, to those who don't. What's that? Sure, they would like the raw ones. So the argument now is that the not meat burger is not necessarily more healthy for you, because they have to put a pile of salt in it and a pile of other chemicals in it to make it work. But, you know, it's not necessarily more healthy. But the people who are making the argument that we should be eating those instead of the meat is an energy standpoint. If you want to be more friendly to the environment, because it takes a lot of energy to put a cow together on the farm. You got to give it a lot of water. You got to feed it a lot of feed, right? And so that takes a lot of energy. But if you just made burgers out of the beans, you wouldn't have that extra trophic level, okay? And you'd be able to feed more people. Now, I grew up on a farm. I'm looking out there at some of you farm guys, and you know, Parker, I think, is going, oh man, I have cows at home. Should I feel guilty about it? No, don't feel guilty about it. I grew up on a farm. I'm not saying don't eat meat. I'm not saying that. But from an energetic point of view, it makes more sense to eat the beans than to eat the cows or the corn. It doesn't matter whether we talk about beans or corn. Because to get to the next level, the cow, it's only extracting 10% of that energy, that food energy, from the beans. Okay? All right? So, if you like the, I can't believe it's not meat burger, that's fine. And if you're doing it because you don't want to kill cows, that's fine too. But in the end, it's not necessarily healthy for you, so you might be doing it to feed more people. Maybe at some point in time on the earth, Jess, warning number one. Warning number one, Jess, put it in your bag. If you're doing it because you want to feed more people, at some point in Earth's population, we may have to do that, right? We may have to remove the cows in order to feed enough people. Yep.
I don't really like the Beyond Meat
burger. I haven't tried it myself.
I like Beyond Vegetable Salad.
The Beyond Vegetable Salad. That's good. That's good. That's funny. That's funny. That's a funny one. All right. Does anybody else have anything they want to add to that? Yep.
Why is it when you can eat, you have so much energy?
All right, I'm going to click this one ahead so that people can write down what's happening here. Yep. Correct. Yes, that's correct. That's correct. I'm not. I didn't want to start a debate on, but you're right. That is a scenario. But I'm just simply saying, as an example of a food energy pyramid, if you're thinking only energetically, do you see what I'm saying? It makes sense to eat the lower level than it does to eat the higher level. But you're right. There's all kinds of issues that are coming into play there. Yeah. Again, this is great, and you know what? In our curriculum, we're supposed to discuss the societal implications of all of the things that we're talking about, but I don't care that much. You guys know that. I'm all about the science. But you're right. You're right. But at some point, our population may get to the point where if you want to feed everybody, it makes more sense for that lower level, right? So then if there's grassland that can't grow beans or corn, put cows on grassland that can't grow beans or corn, right? So that makes good sense because we can't eat the grass, right? But we can eat the corn and the beans. Our bodies are able to consume that. So that makes energetic sense as far as I'm concerned. But you're right. There's all kinds of debate that can happen here. Yes? Correct, because there's hardly any soil on that land to grow a good crop of corn or beans. That's why there's lots of cows up there. Good sense to have cows up there. You bet. Yep, that's exactly correct. Up north, the Canadian Shield, the big rock that is, Canada, it gets closer to the surface of the dirt. And so there's only very little bit of dirt, so grass can kind of hang on and grow there. But a good cornfield wouldn't have enough soil to grow properly. So that's why. Correct. You can't work it. You can't get deep enough. Correct. All right. Pyramid of numbers. So this is simply a description of what happens to the number of organisms at each level. So I could have probably put 2 pyramids on that paper. That was a horrendous fail. But that's okay. Pyramid of numbers represents the number of organisms at each trophic level. This may not always be represented by a regular pyramid. You'll notice that there could be an example of an inverted pyramid. I'm not going to draw an inverted pyramid pyramid of numbers. So again, I'm just making numbers up. But again, at the bottom of our level, we've got our grass. And this is just to put in your notes to illustrate it. But I simply put like 10,000 plants. I don't know if that's true. I really don't know. I'm just saying, let's say 10,000 plants. And let's say 10,000 plants then feeds, and now I'm going to go to 200 rabbits. I have no idea what it takes to feed 200 rabbits. I'm just making it up. You see what I'm saying? But 200 rabbits. So we're literally counting the organisms that need to be fed. And in the end, I kind of said, okay, how many foxes can eat 200 rabbits? And I said 50. 50 foxes. I have no idea. You see what I'm trying to illustrate there? Again, that typically it takes less. And then how many wolves would eat 50 foxes? I put five wolf. 5 wolf. There's some bad English there. All right. Now, again, that's just to illustrate that it takes a lot more of the lower level to feed the next level up. Again, the same argument to eat the not real beef if we want to feed a lot of people. But you know what I mean? It's just, the logic is sound. But again, I'm probably going to go home and have a steak this evening. Who's kidding who? Okay. Notice this one on the chart. It can be inverted. Okay. So this is like one tree. And then on that tree, there are birds feeding off of whatever seeds in the tree. And then on those birds, there could be little insects that maybe are like mites or something that are on the feathers of the birds that are eating maybe dead skin or something like that. And then on those parasites and on those little bugs that are on the birds, there could be all kinds of little bacteria and things that are eating off of the bugs that are eating off the birds. Do you see what I'm saying? And what that would look like is on one tree at the bottom, we would have billions and billions of bacteria on the bugs that are on the birds that are on the tree. So in a numbers pyramid, it can be upside down or even get big and small, not even look like a pyramid. Yes, Jess? Oh, I cut it off. It was a pyramid of energy. I didn't tear my paper off very well. Okay, one more. Pyramid of biomass. Biomass is the stuff of the living thing. All right? When I get into the chemistry unit, one of the first things we have to talk about is what is matter, right? And matter is just the stuff of the universe. It's made out of atoms and, bonded together in various ways. So biomass is the stuff of the living thing. Not that I'm encouraging taking 200 rabbits and burning them to see how much energy you get out of them. Could be interesting. But a bunch of rabbits have stuff, atoms and molecules. And in theory, you could combust them. It wouldn't be nice, but you could do it. So I always think of biomass as being a measurement of how much burnable stuff there is in a level. Don't look at me like that, Jenna. I don't actually go and burn bunny rabbits. But I'm just saying, if you had to, you could.
Why don't you do that?
Well, you wouldn't.
Yeah.
But I'm just saying, that's what this is representing. Okay, so to be honest, it was this graphic that made me think of the whole thing. So you could write this graphic down, but I'm going to put it on the chart paper anyway, because I'm just simplifying some of the numbers. So if this is a pyramid of biomass, we're talking about the kilograms of the stuff. So again, on the bottom here, when it comes to the grass, and I'm gonna change this number up. I have no idea who did this calculation, but I don't trust it. Because we know our scientific notation, right? Times 10 to the 7. But what do all these digits mean? Look at all those digits. Yeah? They've measured super precisely. You see what I'm saying? How many significant digits are in that? 1, 2, 3, 4, 5. Trust me. The guy who made this graph did not do enough experiments to measure the amount of grass that massive snowshoe hare eats to 5 significant digits. So I call BS on that data. I say it's not nearly that precise. So what I was going to put here was, I'll give them a 2.1. I'm okay with 2.1 times 10 to the 7 kilograms per kilometer squared. So they're putting a little area there as well, if we had a grassland of a square kilometer. But for that many significant digits, no way. They did not measure it that accurately. Snowshoe hare. I'm very skeptical about this data, even though I used it. Because look at all they've done. They've simply shifted the decimal. You see what I'm talking about? We're now at 20925 in the 20s of thousands. See how it's the same number? They just shifted the decimal. No one actually measured the mass of the rabbits that you could burn if you wanted to. So again, I'm going to be generous on them, and I'm going to put 21,000 kilograms per kilometer squared, and that's for the rabbits. All right? And the reason I didn't write hare is because I would spell it wrong, like hair on my head. So that's why I stayed away from hair. All right, moving up. Because my spelling is that bad. Fox. Again, notice what they're doing. They're just moving the decimal over. Now, all of a sudden, they wanted to go to 2 significant digits. What? Why? It's weird. So I'm okay with the 2,100 kilograms per kilometer squared. All right? And now I'm skeptical about this top mass. Are we going to produce a greater mass of wolf on the top one than we are next one down? I don't know if that's a possibility. To me, that looks like a typo, but I don't know enough about. See how this mass is greater than this mass? See how the 4200 is greater than that? It's double than that. Would there be a greater mass of wolf in a particular kilometer squared? I don't know. What's that? They're big, but they're getting energy from below from the fox. So how can they get bigger in terms of mass than the fox? Yep.
Well, that mass would be 2 wolves to eat 1 fox.
No, this is in mass. It could be that the wolves are heavier than the foxes. You see what I'm saying? But how can you generate more biomass above if you're only consuming a certain amount of it below? It doesn't make sense to me. I wanted to change that to 420 because, I am not, and that's kilograms per kilometer squared, and that's our wolf, mass of wolf. Again, I'm not an ecologist, so I don't know whether it can invert like this. You know what I'm talking about? Get a little bigger, like the other one was inverted. I don't know whether that's a possibility or not, but if I think about it in terms of what we call conservation of mass in science, that you can't just create mass out of nothing. If these wolves are eating these fox down below, I don't know how they could generate more mass. That's breaking a fundamental law of chemistry as far as I'm concerned in my mind. So I'm changing that number. I'm going to step up and make that change. All right. So your homework for today, you can see you got 20 minutes left. There are some textbook questions that are based on this note, okay? And then you also have that reading, which we will take up on October 1st after the lab on Monday. Yes, Jess?
I'm not going to answer this question.
Okay.
The lab.
The lab, yes.
They're right at the lab, right?
The lab will be a fill-in-the-blank. Here, let me just stop my recording here because the people don't care that much about my lab.